Good morning, everybody who's joined us. For those of you who don't know me, my name's David Bailey. I'm the Chief Executive of Composites UK, and it's been my real pleasure to host today's presentations of the individuals and companies shortlisted for our Innovation Awards. So I'd like to start by welcoming everybody to the 9th Composites UK Industry Awards. This year's awards cover Trainee or Apprentice of the Year, Employee of the Year, the Health and Safety Award, Startup Business of the Year, and the Sustainability Award. And then we have the 3 Innovation Awards: Innovation in Materials, Innovation in Composites Design, Innovation in Manufacture. And today we're going to see presentations from those individuals and those companies who've been shortlisted for the 3 Innovation Awards. However, we won't find out today who has won. So on Wednesday, 18th of November, through social media, through press releases, and then later through a supplement in Materials and Manufacturing Technologies magazine, we will then, Composites UK will announce the winners. It's all very exciting, so let's move on to the presentations. Unfortunately, I think we've lost Richard Thompson, who was due to speak first. So I have warned Dominic that we might ask him to step up to the plate. So shortlisted for Innovation in Materials category, please welcome Dominic Hopwood, Resin Sales Manager for Bitrez, and a presentation entitled FuraCure, PFA Resins and Copolymers, a New Generation of Green Resins. So I invite Dominic to share his presentation and take us through for the next 10 minutes.
Okay. Thank you, David. Good morning, everyone. Can you see the slides on screen, hopefully?
Yeah, we can.
Yes, Dominic.
And is that in full screen as well, Claire? Excellent. So good morning. Thank you very much to Composites UK, not only for shortlisting Bitrez in the category of Innovation in Composite Materials, but also to everybody for joining today to find out a little bit more about who we are and what we do. So just in summary, a little bit about our company for those who don't know. We've been in existence for nearly 40 years. We're a privately owned business with 2 manufacturing sites in the northwest of the UK, either side of Wigan. We are a formulator and manufacturer of high-performance synthetic resins and polymers, formulating materials for 4 key areas: coatings, composites, adhesives, and insulation. And that's based primarily on bio-based thermoset and bio-based chemistries, covering every sector that most people on the webinar will work in. The key element about Bitrez is the fact that we are formulators. We have in-house R&D, and we work in a very customized way, formulating materials to meet the requirements of our customers' process and their application. We have pilot plant scale-up capability, as well as an annual production throughput of around 50,000 metric tons. So to quickly highlight some of the areas where we work in the composite sector. So we split pretty much our business between new material development and also toll processing opportunities, whereby we work with a lot of our larger competitors and also some of the largest material producers in the world. So if, for instance, in the world of composites, we work with a lot of the well-known pre-preg manufacturers, supplying them with our building blocks or toll producing materials to their own recipes. And we also have quite a broad range of technologies for the composite sector. Again, that covers pre-pregs, laminates, and also wet resins for dry fiber processing, covering various different methodologies and various different chemistries, of which you can see some listed there. We typically start at vinyl ester, moving through to phenolics, epoxies, and then into sort of the higher performance, higher temperature materials, as well as supplying complementary curing agents, hardeners, and catalysts. So onto the subject matter of today's presentation and our material for innovation. As the slide suggests, we do have an addiction to oil. Many of the chemistries that people utilize within polymer matrices for composite materials have been in existence for up to 100 years. When we think back to the patent of phenolic resins by Dr. Leo Backlund in 1907, and ultimately we have an addiction to oil. And one of the things I will say is that some people may have seen these slides before, but again, they are very important and they will be used again as we promote the message that the greatest threat to our planet is the belief that someone else will save it. We need to move away from this requirement of using fossil-derived materials to more sustainable supply chains, and that is what our innovation FURACURE is all about. So how has nature provided inspiration? Waste biomass, typically sent to landfill, is now being utilised across many areas within the chemical sector. And of course, within the world of composites, we're seeing a greater development of a range of bio-based materials, from the use of hemp and flax and other waste materials as reinforcements. And the same will be said with regards to the resin matrix as well. So in terms of the focus of our business, it is sustainability is climbing up the agenda and has led to an increased call for materials within the composite sector. So we're a group of 3 companies, all members of Composites UK, who are focusing on novel chemistries utilising bio-based materials, but also very importantly ensuring that these materials are compliant with all the regulatory demands that are placed upon our business and upon our customers' business. So what we're talking about here today, FURACURE, well, pretty much this is a bio alternative to a phenolic resin. They are starting to replace conventional phenolic resins in a number of different applications. There's a range of well-publicised projects through some Composite UK members. But traditionally, that supply chain of the PFA resin system has been from overseas competitors, and as obviously Composites UK will advocate, we are trying to build a supply chain for the composite sector here in the UK. And so the switch to developing a range of polyfluoroalkyl alcohol resins, which obviously offer similar performance to phenolics, was the key objective of this innovation. So supported by our partner CPS, we've developed a range of polyfluoroalkyl resin systems, which are, as the schematic shows, there's a number of ways in which you can derive the sugar element of the PFA resin. In our instance, we use corns and corn cob husks, and what we have is a resin material with a very high bio-based content, which, as the previous slide suggests, cross-links in a very similar way, offering some of the benefits and performances of phenolic resins. One of the things that, as a group of companies, we're very keen on doing is looking at not only the sort of bio-based content of these resins, but the whole principle of green chemistry. And back in the 90s, there was a document, a framework, should I say, developed to look not only about where does the material come from, what waste stream does it come from, but is it ethical, is it sustainable? And this is something very much that we as a business are working towards, to ensure that it's not just simply about utilising the bio-based materials, but that they have a significant impact on reducing carbon footprint and increasing the benefits to the environment. One of the key credentials, though, of course, is the bio-based content. And what you can see here is a screen grab from a third-party independent testing laboratory, which is running a test, ASTM D6866-20, which is a way of determining the bio-based carbon content of a material when compared to the fossil-derived carbon content. And as you can see here, the PFA resins are 100% bio-based, which obviously is certainly good in relation to our work around the 12 principles of green chemistry. Moving on to sort of the benefits of the innovation, aside from the environmental credentials, The PFA resins offer the same flame retardant performance as a phenolic. These materials are polymeric, and so they are REACH compliant. They have an absence of substances of high concern, unlike traditional phenolics where we have phenol and formaldehyde. And of course, formaldehyde is a very dangerous substance if inhaled. We are able to replicate the performance of phenolics without the formaldehyde. And whilst the furfuryl alcohol is again a toxic material, we're driving those contents down to less than the threshold of 0.1% free alcohol. Very good temperature and chemical resistance and outstanding acid resistance. And whilst, of course, we're sort of targeting the two key areas of pre-preg manufacture, which is the hot melt and the solvated routes, we're also in the early stages of sampling and developing low viscosity systems for infusion and layup. Isn't without challenge. These materials are very pH sensitive, and the acid catalyst required to react them is a very delicate process indeed. But we see this as a fantastic opportunity for our business to increase our environmental footprint, improve our environmental footprint, and obviously support the UK composite sector with bio-based and more sustainable materials. And that's it from me. If anybody has any questions, then feel free to join the Bitrez table later on, and I'll be happy to answer any more detailed questions.
Thank you, Dominic. That pie chart of 100% bio-based versus fossil was very clear. There was no debate there, was there?
No, none at all.
Okay, so as Dominic said, at the end of the presentations, everyone will get an opportunity to join the speakers on the tables provided by the Air Meet application. So we'll get into that later. Do we know if we've got Richard Thompson back?
We seem to have lost him completely, David, so I think we just move on to Sam.
Okay, so we'll continue to try to get Richard back into the Air meeting. So we'll move then on to presentations for those shortlisted in the Innovation in Composites Design category. So our next speaker is Samantha Bunyan, founder and head of industry engagement for Cecence, and her presentation is the world's thinnest economy sustainable seat back. So over to Samantha.
So thank you very much for inviting Cecence here to talk to you about our nominated entry in the Innovation in Design Award. And it's for our work on the development of what is believed to be the world's thinnest sustainable economy seat back. So if you can just forward the slide. So just a little bit about Cecence. We were founded just under 8 years ago on the Wiltshire-Hampshire border. We have a very innovative and agile approach to the manufacture and development of lightweight FST compliant components. And we are very proud of our largely locally based team and our sustainable manufacturing processes. We have an RMRA, right material, right application philosophy, which enables us to select the optimal fiber and resin combination for each application that we're working on. Next slide, please. So the award we've been nominated for this year is the result of a NATEP project where we developed an affordable, and I think that's probably one of the most important parts of this, that it's an affordable option of an ultra-thin, lightweight, sustainable aerospace interior seat back. And it's maybe useful to talk briefly about the landscape within which this innovation sits in order to reinforce the need for the approach that we've taken on this structural component and which we continue to take with the development of our other new products. And COVID-19, as everyone is aware, continues to economically damage the travel sector. Consumer pressure is being put on airlines by passengers who are now better educated about climate change. And the Swedish have even created a new word, flickscam, to describe flight shaming. And so, as Dominic was talking about earlier, there's a real need and opportunity to demonstrate our commitment to the environment. And at the same time, the UK government's ambition to achieve net zero carbon emissions by 2050 has succeeded in reinvigorating the idea of a circular economy. And in the manufacturing sector, there has been a renewed interest in the use of sustainable materials and sustainable production methods. Next slide, please. So consumer pressure will inevitably push for these new eco-friendly materials to be introduced, and the growth in recycled and renewable lifestyle products, a move away from fast fashion, an increase in electric car ownership would suggest this to be the most likely direction of travel. Next slide, please. So to meet these environmental demands and the demands for future air travel, we'll need to look for lighter recyclable components aligned with alternative fuel systems such as hydrogen and electric flight. And there has been a great deal of development in greening the aerospace sector, but it's been predominantly focused to date on the development of alternative biofuels and the recycling of in-flight consumables. Our composite manufacturing focus has been on lightweighting the cabin using carbon and glass fiber to save on fuel burn. Next one, please. So whilst structural and semi-structural aerospace lightweight carbon and glass fiber composite components have started to be embraced by the aerospace industry, they're still largely reliant on the use of phenolic resin systems. By integrating bioresin for future aerospace interior products, we can reduce the carbon footprint of the aircraft's fuel burn and encourage much needed investment in ideally a homegrown supply of sustainable resin systems. Next slide. So traditionally, phenolic systems have not had the structural strength of epoxy systems. For the development of the ultra-thin seat, Cecence integrated carbon fiber with a bioresin supplied by SHD and achieved both clear FST compliance and strength. Early use of non-destructive testing through partnering with wavelength NDT as an integral part of the development process allowed optimal materials to be selected from a really early stage in the development process. And the basis of this research, combined with Cecence's composite material, structural engineering and processing know-how, is very much at the heart of this innovation. Next slide. Thank you. So Cecence were awarded support through NATEP in the form of 50% of the development costs for a project entitled Low Cost FST Compliant Composite Components. ATI have recently increased NATEP funding for SMEs to 70% to stimulate further innovation during the pandemic and economic crisis. And the 18-month project was completed in early 2020 and initially had set out to develop a relatively small structural subcomponent of an existing seat design. Next slide, please. So as the project developed, and through our partnership with SHD Composite Materials and Wavelength NDT, we could see the potential to not simply focus on the originally selected smaller subcomponent, but to look at how we might take the early analysis and study and apply it to a whole seat back. And this in turn provided the encouragement for Design Q to work closely with Cecence on the development of an entirely new, larger structure, excited by the discoveries that had been made during the project and a greater understanding of how carbon fiber and bioresins could provide a more radical weight-saving and, critically, sustainable design. Next slide, please. So Cecence's practical approach and understanding of how to industrialize composite production through its proprietary preform and processing methods produced a seatback that was slender, incredibly light, strong and sustainable, and the component is designed to be compatible with an existing seat frame structure, which helps to drive down costs for the airline in terms of upgrades to current seating. Next slide, please. So the innovation will enable more legroom and fit with the needs of today's commercial airline passenger. The 7-kilogram weight of the design saves at least 500 kilograms per flight on an A320. The seatback's bioresin carbon composite offers an opportunity for the airline to demonstrate its eco-credentials to today's eco-savvy customer and to support a circular economy. And the resulting product is a great example of driving innovation through a collaborative approach. Thank you very much for listening. Please make a note of the contact details, but more importantly, or maybe less importantly, or equally importantly, come and join us at the Cecence table. And can I use this opportunity to thank Composites UK for the nomination and wish every company who's been shortlisted for this year's 2020 virtual awards very best of luck.
Thank you, Samantha. Excellent presentation. I'm a big fan of the NATEP project. I've worked on it myself previously. I think it provides companies with lots of help and support beyond the funding. I'll come to your table later to talk about that 500 kilogram weight saving, what that's worth in terms of fuel burn, and what that's worth in terms of carbon saving. That sounds like a really interesting technology. Thanks, Samantha.
Thank you, David.
Okay, so our next shortlisted individual and organisation in the Innovation in Composites Design category is Alan Banks, Head of UK Innovations for Ford Motor Company. Alan's going to present on the chassis project, composite hybrid automotive suspension system, innovative structures. Over to you, Alan.
Good morning, everyone. I'm going to attempt to share my screen. The last time it did this, it didn't work, so we're going to give it a go. Excellent, that's good news. Okay, thank you, everyone, for joining. Again, the same as everybody else, I'd like to thank Composites UK for the nomination and the shortlist. This is a project that we're very passionate about and we're very excited about at Ford Motor Company. We started this project based on a previous project that we did with Innovate UK called CLASS, and this is the natural progression from that. So chassis stands for Composite Hybrid Automotive Suspension System with Innovative Structures, and what that basically means is we want to demonstrate the hybrid material approach on mainstream vehicles, understanding that certainly in the short term, a full composite material part, whilst probably feasible, isn't necessarily the right thing to do from a business perspective. But from a commercial vehicle, we start to get more into the business aspects of this, because every kilogram that we take out of a vehicle means that we put it into payload. And as a major OEM, we charge for payload. That's where we get our money. So the more we can put in the back of a commercial vehicle, the more we can charge for it, which means the more we can spend on getting that weight out. We are looking at full mass production to suit 500,000 vehicles a year. We have a cost target to take the weight out of $9 per kilo. That's actually quite a high target. Also, we at Ford we have paid that in the past, but that's quite the high end. But we wanted to make sure that we got a really, really good project out of this, so that was our cost target. Our cycle time is to ensure the full mass production of 500,000 a year, as I said. So the cycle time needs to be sub 5 minutes for every component, and we wanted to take out an average of 40% from all three of those components, with the technical challenges being obviously the vehicle needs a full sign-off sort of design verification, which includes stiffness and strength. Next slide, please, Claire. So these are the components in question, as I said. The steel parts, the current production are on the top, and the hybrid components are on the bottom. And as I said before, these are a hybrid of components, bearing in mind that a full composite solution, whilst sort of technically possible, isn't really affordable for a mass production OEM at this time. Next slide, please, Claire. So I think, as this is no great surprise to everyone, with regard to a composite set of components, not only do you get the lightweight out of it, but you can also decrease the complexity of the child parts that go in to make the assembly. This is enabled by our right material in the right place philosophy. Across all three components, we save 56% of the actual subcomponents that go into making it. So our rear dead beam axle that would normally take around 16 components is now down to 8. The front lower control arm that is now made, which is fabricated and welded and has 5 components, is brought down to 3. And the front subframe, which takes almost 30 components, is now down to just over 10. So that really does simplify the part manufacture itself. It takes out a lot of the expensive welding operations that we have that can have sort of inherent sort of quality issues as well. So this actually helps quite a lot for our plants and our suppliers. Next slide, please. So the front subframe is actually a hybrid of materials with high pressure die cast aluminium side rails, with a pre-preg SMC carbon fiber rear panel. It has carbon fiber pre-preg upper and lower panels, 3.5 millimeters on the top, 3 millimeters on the bottom, with an aluminium extrusion in the front panel. That's all going to be sort of structurally adhered in a jig. Again, this means that we have the right materials in the right place. All of the load paths are taken care of. The adhesive bonding is completely assured via the processes that we have that's being trialled by the University of Nottingham. All of the tolerances for this part are taken into account as well. And again, we have 18 less components in this assembly. Next slide, please, Claire. The front subframe itself, our CAE studies, this is one slide to show what is basically 3 years of work, so apologies, it's down to one slide. All of these stiffnesses that are required for this part, bearing in mind that this holds the lower control arms, this is where the suspension is effectively mounted to the body, were all taken into account. They had to meet all of the design practices of the steel part, so we didn't leave anything behind. And this part, so far in CAE, has met all of our requirements. Next slide, please, Claire. The front lower control arm is actually a mix of materials. So this is we have an injection molded inner core, which is a PA12 nylon with long glass fiber, hence it's white on the inside of that, as you can see. And that overmolds a steel insert, which is for the knuckle ball joint that we couldn't make out of carbon fiber, just because the size and weight and the duty cycle of the vehicle meant that we would exceed the hoop stress of that taper. So that's steel part as it is in the current fabricated part. That's overmolded by the inner core, and then that whole assembly is overmolded again with a PA12 nylon long carbon fiber, hence it's black on the outside. Again, that component reduced its sort of subcomponent count sort of by 2 parts. It's going to save around 29% of the weight of the steel part. After this, we insert the bushes as we would normally do on a post process, as we would do with the steel part as well. Next slide, please, Claire. Again, one slide to show you 3 years of work, but clearly the lower control arm is very important. It holds the wheel on, so it's very important that we maintain the static stiffness, the buckling, the strength loads, and its durability. All of our targets were met on this particular part. It took quite a lot of design development to make sure that we were sort of in the box with this part. The lower control arm, as I said, holding the wheel on, it's a very, very sort of sensitive part with regard to manufacture. But this part far exceeds the design of even the steel part, so we're very happy with this one. Next slide, please, Claire. Our rig dead beam is actually a new process for me. I mean, we'd heard of it, but I'd never really seen it up until the point we started this. So this part is actually going to be through the pultrusion process. It's made up of 3 different composite materials, which is on the inner side we have a triax carbon, then in the middle we have a UD glass, and that's all molded over the top with a woven carbon. All of that goes through the pultruded machine. We save 53% of the weight of this component, which is quite tremendous, really. This has 8 less components in its assembly than we would have on the steel part that it replaced. Again, with the philosophy of the right material in the right place, all of the load paths to meet the strength requirements of a rear axle are met. We actually just make 1/2, so I don't you can see my cursor, probably not, I'm not sharing, but we only make the one section, which is the section with the labels attached to it. That's then mounted back to back to actually make the beam so that we can sort of fulfill the strength requirements. And this is all adhesively bonded in the jigs at the end of the process. Next slide, please, Claire. And again, our CAE predicts that we're not going to have any issues with this. We actually have extruded aluminium. I've lost your screen, Claire. Hopefully it will come back. Oh, there we go. Thank you. This has extruded aluminium ends that hold the wheel bearing carrier, the spring seats, and the jounce bumper reaction plates, and the whole thing is assembled with adhesive bonding to meet the vehicle integrity. Next slide, please. So we have a pretty good LCA analysis on this. We get payback in CO2 from cradle to grave on this within 3.35 years for the front subframe, in 1.3 years for the control arm, and just over half a year for the rear dead beam. Now, the differences in those are due to the manufacturing processes of the materials that we have in there. So the front subframe, although it saves quite a lot of weight, it has UD sort of pre-preg in there, which is a very CO2 intensive process to manufacture that part in the first place. Hence, that one's sort of quite CO2 intensive, and the paybacks have been 3.35 years. On the rear dead beam, of course, we still have triax carbon, and we have woven fabric that goes over the top, which again is still quite CO2 intrusive to actually manufacture those parts. But because of the amount of weight we save, we get payback over just over half a year. Next slide, please, Claire.
You've got 1 minute left, Alan.
Thank you very much. So in summary, you'll be pleased to know I've nearly finished. Our steel parts are on the left-hand side. Excuse me. All three of those together weigh just under 70 kilos, and they've been developed over many years, and they're optimized for the vehicle, so there's not any weight to take out of those. But when we reverted to the composite hybrid solution, we actually reduced the weight of those parts to 38.7 kilograms. So that's a 44% weight saving compared to the 40% target that we had. So we saved just over 30 kilos. Next slide, please, Claire. So as you can see, we met our cycle time for the volume production on all three parts. We've achieved our 40% weight saving. We've got 56% reduction in the assemblies. Our CAE process has predicted that we will have a really, really good result at the end of this. And manufacturing will be done on exactly the same test rigs with our supplier Gestamp, who make the steel parts. So they will be sort of tested back to back on the production rigs. We've achieved all of the CAE targets, and our costs are fully in line with our $9 per kilo target. We'll start the manufacturing and the trials of this in early 2021, and we expect to have a really good result when these parts go on a vehicle. And the last slide, I think. Excellent. That's just our contact details. We'll be happy to take questions when we have the breakout sessions on the tables. Again, thanks very much for the nomination. Really, really appreciate the support from all of the partners from Gestamp, National Composite Centre, and the University of Nottingham. Thank you very much.
Thank you, Alan. Very comprehensive presentation. Do I assume that as you take weight out of those parts, that allows you to put more weight into the back of the van?
That's absolutely correct, David. That's the entire raison d'etre of this project. We want to get more commercial vehicles off the road.
And so do those parts have to then perform at a higher rate than the parts that they're replacing because they've got more weight in the van?
Yeah, they do. That's accounted for in the designs, as you might expect. They obviously have longevity as well. So once the vehicle's past its useful life, those parts are not. They've still got many years left in them. So we expect to see those parts appear in the aftermarket for older vehicles that need servicing. So we think this is a project that has kind of a real sustainability effort in it, as well as just CO2. We can reuse these parts in the aftermarket.
Absolutely. Thank you, Alan. Okay, have we got Richard Thompson back?
We do indeed.
Okay, so I think it would be appropriate to go back to the category for those shortlisted in the Innovation in Materials category, and to welcome Richard Thompson, Commercial Director for Alvant, whose presentation is on reducing landing gear component weight by up to 30%. Welcome back, Richard.
Hi, David. Yeah, thank you, and apologies for dropping out literally 30 seconds before. So yeah, what I might do is I'll share my screen and do like the other guys. And what I might actually do is just turn my camera off for fear of anything dropping out again. But obviously, I'll keep my mic on. So yeah, Claire, if you just tell me if anything drops out.
Yeah, will do.
Hopefully it won't. Okay. So I'm not sure if you can see my screen.
I think it's coming.
Yes.
Yeah. Okay. Excellent. Yeah. So many thanks for the nomination, and we're very excited to be in the mix with some companies with some really innovative ideas. So I'm here today to represent Alvant, and also recognise that we're in the growth stages of a new age, and one that's not characterised not only by the digitalisation and Internet of Things, which doesn't always work sometimes, but more importantly by new materials, and these materials that can make our future easier, safer and more sustainable. And what I'll do is I'll give a quick intro to the company and the materials, the specific materials that we focus on, mainly because not everybody's aware of them. They're a little bit unique, and then obviously quickly move on to the project in partnership with Safran. So Alvant is classed as an advanced materials company, and we focus on aluminium composites. And our mission is to be a catalyst really for sort of material evolution, or be part of it, and increase the capability of the world's most demanding products through the application of advanced materials and manufacturing techniques. So our core competence is the application, design, development, manufacturing, the application of these AMC materials into highly engineered products. And as you can probably imagine, we have a range of capabilities to allow us to do that, from materials engineering through to the other end, where we want to obviously get these materials into market. So it can be a combination of manufacturing and licensing. So, what is an AMC, an aluminium matrix composite? Well, they're not similar to carbon composite. They're not a single material. They're a family of materials, and the properties can be tailored through the matrix, the aluminium that we use, and also the reinforcement selection. But in essence, the underlying thing is these materials are lightweight and can provide the strength of steel with the weight of aluminium. That's the whole concept of them. So essentially, we bring together aluminium with a high performance ceramic material, and that can vary in format and type. And out of the other end, we create this essentially a metal composite, an aluminium matrix composite. And the benefits of these materials, as I alluded to, they can give you the strength of steel or titanium, but at 1/3 of the weight. If you're comparing it to more aerospace type of aluminium, say a 7000 series, we can, we've got tests that we've run with customers where we've had 4 times the fatigue strength. And one particular customer wanted us to do a back-to-back test, or they actually ran the test, where they were looking at their component, and they wanted to compare our material against a 7000 series aluminium, and where their current material failed on this particular test at around 50,000 cycles, they actually stopped the test at 10 million cycles with our material, because I think they needed to free up the rig to do some other work, and I think we proved the point. So they're very sort of fatigue and damage tolerant, and depending on the variety of the material, they can enhance the wear and corrosion resistance, and you can also tailor the electrical and thermal properties. So they're exciting prospect and material with, as you can imagine, lots of applications across lots of markets. So at Alvant, we have a patented process how we actually manufacture the materials, and that provides us with 4 material families, and we've given them brand names here. So our Alzal material is a high strength lightweight material, and that's a continuous fibre. We also have a very unique sandwich material, which we call Corzal. We have a syntactic foam, which is called Airzal, which is about 1.5 grams per centimetre cubed. Syntactic foam essentially is a metal foam with glass microspheres. And finally, Parzal, which is perhaps a variety of AMC which people are more familiar with if you are aware of them, which is a particle reinforced aluminium, and that's typically silicon carbide particles, and it gives you very good wear resistance, very hard wearing, so abrasion resistant. So overall, the overarching sort of value proposition and why we are working with Safran on a particular project is the whole concept of being able to enhance the capability of a product whilst respecting the sustainability targets. And that's as Samantha and the other guys have alluded to, is to combat the growing challenges around trying to achieve a net zero by 2050, legislative demands, and also, you know, to place UK at the forefront of technical innovation, and also interestingly with the continuous fibre AMC or Alvant material, it has potential for recyclability. We can separate out the aluminium from the fibre, but ultimately, because of the lightweight nature, it can help reduce your fuel consumption and carbon emissions. So overall, we have this overarching value proposition of sustainability with enhanced capabilities. So as you'd imagine, you know, lots of applications and lots of markets. But currently, we're focused on electric machines and links, struts, and structures. And today, I'm going to sort of just dip into the project we've been working on with Safran, which is more on the links, struts, and structures side of things. And at the bottom there, as you can imagine, no surprises. You know, we're into electrified transport, aerospace, power generation, and motion control type of products. So yeah, our nomination for this award is based off the work we've been doing with Safran Landing Systems on a large Innovate UK backed programme called Large Landing Gear of the Future, and it's a 2-year, £28 million project. And our contribution to the project is to look at a brake rod, connecting rod, which is in the landing gear. So hopefully the image on the right, you can kind of sort of see underneath the wheels there, you have these connecting rods or links or struts, which link the sort of the front wheels to the back wheels, the braking system side of things. And our target is to try and reduce as much weight and replace titanium. So typically, if we're talking about aerospace, we are typically tasked with displacing titanium components for various reasons. And so our goal is to achieve a significant weight saving whilst also achieving the same sort of design allowables as titanium. And Safran are obviously guiding us and will be also responsible for testing the component in the latter stages of the project. So exactly like Samantha said, it's all about reducing weight, fuel burn and noise, improving the reliability and obviously lowering operating costs for commercial airlines. And typically, you know, because of the safety requirements, particularly landing gear systems, you know, they're sort of over-engineered, you know, and that means that, you know, typically sort of wet finger in the air, landing gear can equate to or be responsible for about 3% of the aircraft weight. So, and of course, once you've taken off or you've landed, the landing gear is a bit of a parasitic loss, really. You're just carrying this massive weight around, which isn't doing too much unless you're landing or you're on the ground. So it's a good opportunity to look at how to take some significant weight out of those systems. So our solution and where we are today and what our nomination is about is the work that we've done to date. And similar to Alan, you know, we've boiled it down to one slide, but, you know, a lot of effort and work over you know, more than a year has gone into this. And so from a timing point of view, we're currently at quarter 17 of a 23-quarter project. And where we've got to our design, our simulation, validation work that we're doing is indicating that we're on target to achieve a 31% weight saving on that particular component. And we've done that with some innovative, unique way that we design the fibre architecture, which you can't really see. You know, we're a little bit sensitive to some of the IP around this, but within that component, there's some unique fibre architecture and how we actually create the preforms. In this particular example, we've used a robotic fibre placement technique, and then we use our proprietary process, in-house proprietary process, which we call advanced liquid pressure forming, to create a near net final part. So yeah, we've completed a series of element level tests to date to demonstrate the capabilities of the manufacturing technique and validated the predictions from the FEA modelling. And we're scheduled to test in 2021.
You got 1 minute left, Richard.
That's good, because that's my last slide.
Excellent timing.
Yeah, exactly. So yeah, thank you for listening. I appreciate it was a quick canter through, AMCs and the project. But by all means, contact me after the presentation if you'd like to learn a bit more about the company materials or the project. So I'll end it there.
Thank you, Richard. That was a really interesting presentation, and it's great to see very different materials being used in this strategy of reducing weight in aircraft. I often thought it would be carbon fibre materials that would be used in landing gear systems, but great to see the work that you've done. I'll come and talk to you later on your table. Thank you, Richard.
Okay, no problem. Thank you.
Okay, so we'll now move into the shortlist for innovation in composites manufacture. Our first speaker is Peter Quigley, Engineering Manager for CCP Gransden, who will present on an advanced single-stage overmolded CF PEEK thermoplastic composite access panel for aerospace applications. Peter, just to warn you, I think Claire is probably going to stop you midway through your presentation for the 11 o'clock 2 minutes silence. So apologies for that, but we do think it's important to respect that. We'll try our best to pick the presentation back up with some energy and momentum after that. Thank you. We can see your slides.
Thanks. Sorry, just getting used to technology here for the first time and using this. So, yes. So first of all, thanks very much to Composites UK for the nomination. What is our innovation? Our innovation is single-stage overmolding. It's been a long route. This is not something that's happened in the last 6 months. So it's culminating about 5 years of work, and it's culminated into a carbon fibre PEEK access panel, representative access panel focused on aircraft structures. But you can take that demonstrator and apply that technology in multiple places. I'm not going to get too much into the technical on single-stage overmolding. I could be here for about an hour talking on that. But really just to give an overview of what we've been up to. So, what do we do at CCP Gransden? Well, we're a manufacturer of advanced composites. We, like some of the themes before, we believe in the right material in the right place, having the right process for the application. So we don't just do thermoplastic process here. We have a range of processes that we can work with, and that means we can deliver the right process optimized for our customers' needs. Our end goal is production, but what we recognize is we do have to get involved at the very start of programs so we can drive the DFM and drive efficiency into the component. We are active across multiple sectors, so aerospace, automotive, security and defence. And whilst that's quite different, they're quite different sectors to be involved in. There's actually a lot of good synergies between them. It's been very useful for the development of the single-stage overmolding process. One of the key areas is around qualification. So aircraft structures, we know that is a hard challenge. We know we need material qualifications, process qualifications. Airbus, Boeing need to be involved in that, and that's a long process to get to that point. However, aircraft interiors qualify products differently. So the qualification process is significantly shorter, and defence in particular can be as short as a 1 or 2 month qualification program. So we can use the different sectors to our benefits and the diversity of the qualification approaches to really advance this technology. Also gives us views of a lot of different applications of this manufacturing process. So taking on a journey from 2015, we as a company, we've been around for 125 years, believe it or not, but in 2015 we moved away from what we call a GFRP, large industrial sector assemblies, components to focus on aerospace, automotive and defence. 2015 we took on the NATEP project, and in that you see the demonstrator lines in the bottom left. We were able to realise thermoforming of pre-consolidated thermoplastic laminates. That's taking a Torre or a Tejan laminate and press forming that. And that is a flying technology today. Okay. In 2017, we took on a large investment program. I was part funded by Invest NI, and we looked at multiple different technologies in that. One of those technologies was single stage overmoulding. In 2017, we were able to successfully manufacture PPS injection molding compound, injection molded in a single stage onto a PPS laminate. That was a good success. A lot of people have seen this component, because the next stage was take that to market, get that in front of the OEMs. So 2018 has 19, even to today, is by getting this technology in front of customers. In 2018, not solely focused on single stage overmoulding, but we did enter into 2 large programs, one with Jaguar Land Rover and another with Bombardier, focusing on these high rate technologies that we have. So we didn't stop there, we've kept going. In 2018, we managed to do peak on peak, the third picture across at the bottom. That was on the same tool demonstrator, but there was a lot of things which we still needed to perfect and develop in terms of the manufacturing process. In 2020, we were able to move forward and manufacture a aerospace representative component, and that's been working with the aerospace primes to develop that, make sure it's customer focused. So what's the cell that we do this on? It is a high rate advanced composite manufacturing cell. It's here, it's in our factory, just outside Belfast. It's a large press, an infrared oven, robot. That allows us to do the thermoforming operation, but integrated into that is an injection molding unit, or an HPRTM unit. And it all comes together in a single cell, so we can combine these processes as we need to. So thermoforming, we're taking a pre-consolidated laminate, we're heated in the infrared oven, heat that up to melting point 400 degrees Celsius. We do that in an optimized oven, so we achieve that in about 1 or 2 minutes, depending on the thickness of the laminate. We then transfer that rapidly into the press whilst it's still molten, and press form the component to shape. So that's thermoforming, a process in its own right. But what we then do is single stage overmoulding. Whenever it's in the press, we then open the injection molding unit, and we inject a shot of injection molding grade, similar to same as injection molding, carbon filled, glass filled, 30-40% polymer. And we inject that in. Now we do this in a single process. The benefit of this is the laminate is in the molten state. The polymer coming in is also in a molten state, and that creates a melt-melt interface, and that's what gives us what we believe is a performance improvement over a 2-stage overmoulding, where you have a warm, solid laminate and molten polymer. So we look at our 2017. What benefits does this technology have? If we look at our 2017 demonstrator, well, we try to encompass as many things as we could into this demonstrator: localized targeted stiffening, the ribs, structural optimization, targeting load cases. And what I mean by that, when in aerospace, when we design a component, there's multiple load cases, and if, for example, the load case defining the thickness of the laminate is bearing, the whole laminate then has to suffer that thickness in a thermoplastic component. With single stage overmoulding, we can target the area where you have those bearing loads and reinforce that with overmoulding compound. We also then have part reduction, incorporating bosses and assembly features. I'm really trying to get the cost out of this. It's through integration that we have to drive, that we get to get cost saving. And the other great thing about single stage overmoulding, we're not using 2 different polymers. We're using the same polymer. So there's very good opportunities for end of life recycling of this aerospace material. What we've been working on since then is taking this a little bit further. So this is what we've entered for the award, single stage overmolded aerospace access panel demonstrator. Some unique features in this. Again, we are looking at targeted stiffening and changing the ribs. You see the change of geometry in places. But in this case, we also do a peripheral sealing. So we inject polymer around the periphery of the part. It's net molded in, which reduces material wastage, but it also removes a step in aerospace which requires edge lacquering. It's another process step which is eliminated. This part would come out of the press after 3 minutes and go straight into CNC for drilling holes. And there's even potential in the future to improve that as well. So reducing CNC time, reducing lacquering and additional steps. The other good thing about this is aerospace qualified materials. We haven't deviated from that. So what's the challenges to the route to market? In aerospace, these are the same challenges, and these will be here for a couple of years, but they are being addressed by industry. Characterization of the joint. How strong is the joint? Qualification of the process. Again, we need to go right up to the Airbus, Boeing level to work on the qualification of this. They need to decide how are they going to qualify the process. Simulation of the process, development of stress tools, and the other big challenge is NDT versus statistical process control. How do you know you've got a good joint, a good bond whenever that part comes out? We collect thousands of pieces of data on our cell, but will that be enough, or do you need to move towards NDT? And how do you NDT something that's got two different material forms in it? So those are challenges which really need to be addressed in aerospace, but I'm pleased to say they are being addressed. In automotive, aircraft interiors is slightly different, really because of the way components are designed and qualified. What do we need to move forward? Opportunities, commitments from OEMs, that's from automotive aircraft interiors. There's small opportunities out there, low risk, and we need to just move forward and start doing this. We need some easy wins. We also need to look at the material supply chain. We need production lines that are big enough to supply the need, but we also need big enough need from the OEMs to drive more efficient production lines. Bit of a catch-22. We need to look at material costs, and also we need to consider e-coat. So whenever we do this with nylon materials, can that product go down through the paint line? So last slide, I've left the sales pitch to the very end. But so CCP Gransden, we're not just thermoplastics manufacturer. We have a range of capabilities from high rate to low rate. The only thing we don't do is autoclaves. So this brings my presentation to a close. I believe we'll have time in the seating area afterwards to take any questions.
Thank you, Peter. Fascinating presentation. I agree that qualification of the process for structures will be painful, but you're working with Bombardier and you're working with Spirit, about to become one in your part of the world, so you're working with the right partners.
Thanks, David.
Okay, so moving on to our last but not least presentation in those shortlisted in the Innovation in Composites Manufacture category. Delighted to welcome Andy Whitham, Technical Manager for Cygnet Texkimp. The presentation's on the world's first commercially available thermoplastic manufacturing line capable of using standard thermo to create high-grade thermoplastic prepregs on an industrial scale. Over to you, Andy.
Yeah, thank you for the natty title. I'll just share this screen. I hope everybody can see that.
Yeah, that's there, Andy.
Brilliant. Right, well, I'll begin then. So, as Peter just mentioned, we've got the shortlist for the very long title there, but I'll skip over that and simply call it the direct melt impregnation line. Thank you very much for the shortlisting. Thank you much for everybody joining in. So who am I? That might be a good place to start. I'm Andy Whitham. I'm the technical manager for Cygnet Texkimp. I've been making bespoke or special purpose machinery since I left university, which is far later, or further back than I would like to admit. And fundamentally, the reason I'm here talking today is I'm responsible for the R&D element of what we do here at Cygnet Texkimp. What's a Cygnet Texkimp, you might ask? Well, we are a very smallish machine builder based in Northwich in Cheshire, down close to Manchester Airport. We've been making essentially textile processing machinery from 1974 onwards. Started with creels, which is essentially the machine for unrolling fibre from a bobbin. About 10 years ago, we moved into web converting, which for the purposes of this discussion is pretty much pre-preg machines or a coater, for example. So we've done quite a number of those recently. We also do slitting and spooling, which is the converting of that material into high precision tapes for, say, AFP or fibre placement mechanisms. We also do filament winding, so that's pretty much using all of that stuff to wind around a mandrel. Fairly significantly for us, we do automation and handling, which is pretty much everything that makes running a line of that ilk convenient, so automatic unloading, automatic loading, right through to the full, this is an automatic line where you essentially throw raw materials in at one end and a part pops out at the other. And last but not least as far as I'm concerned, the special projects and research element of what we do, they do go hand in hand. Special projects even are simply a project that's got inherently a fairly low TRL level and it requires a little bit of research to complete. So fundamentally where we walked in was pre-preg machinery, which is the production of a pre-impregnated carbon or glass or multi-filament band, sticking a resin or some sort of matrix within that and processing that downstream. As you can see there on the screen, I hope is a standard-ish thermoset line. Clearly quite a significant beast. It's 624 millimeters wide, if I recall correctly, and about 20 meters long. And that's basically taking carbon fibre, in this case, from the bobbins and making a sheet out of it. Nothing more spectacular than that. However, we some time ago started to realise there was this thing called thermoplastics. And while we've been fairly successful in the thermoset arena, we, as a machine builder, really realised that there was potentially benefit in having a foot in both camps, thermoplastics and thermoset, so that we covered that. We have a research and development department here at Texkimp, and back in 2014, we really started to get serious about actually doing something with thermoplastic composite. So we developed a thermoplastic line. This is a picture on the left-hand side there from our current research and development facility. It amounts to about £250,000 of equipment investment, which for a company of 70 people is relatively significant. But we did this with no fixed idea on how to process a thermoplastic tape. We therefore didn't know what polymer we would be using, what form it would come in, what type of fibre would we be using, would it be UD, would it be woven? UD means unidirection. Would be having carrier media, or would we be experimenting, for example, with metallurgical release coatings to get the thermoplastics to leave the parts within the machine? And in reality, we didn't really know what the machine was going to look like. It's fair to say that that machine is no longer representative of our state of the art in terms of our understanding of how to make a thermoplastic tape. So I suppose the world's first part of this is the direct melt impregnation system. I've got a little schematic there on the screen. You've got the fibre input on the left-hand side. It's relatively straightforward for us as essentially fibre handling experts, we like to say, to create a continuous sheet of fibre. So we're using pretty much the same technology we'd use on our thermoset prepreg lines and the standard creels that we offer as a range. So that is presented, if you like, to a coating section. We coat top and bottom, or top or bottom, depends on what we're trying to do, the nature of the polymer, and what we're trying to achieve as an end result. So we're not using any special polymers, it's literally pellets or powder. So we're using standard extruder technology to create a sheet on top of or underneath the fibre substrate. We then have an impregnation box, which is simply a little bit sensitive, but it essentially adds a lot of heat. This does exactly what you'd expect it to do, being called an impregnation box, and it forces the polymer within the fibre bundle. When we finish doing all of that, we have some finishing rolls, which essentially freeze the polymer on the fibre and give us some tape consistency. We want the material to actually look quite smooth and pretty, for want of a better phrase. Clearly, there's not a lot going on there. It's fairly short as a process. So in comparison to the previous thermoset line, this line is less than half of that length, including the creel. And it's fair to say also that we have used a vast range of polymers in this process. We started off with polypropylene, and of course, everybody wants to have the glory of being able to run peak, and I'm pleased to say that we have done that too. So here we are with a picture of the actual line we developed and supplied recently. It's got all of the features that you've come to wish for over the last 6 years of developing several generations of this kit. It is essentially electrically heated, which is a major feature from our perspective. Allows you to get the temperatures. It's a very clean solution, and it gives us really good control of all of the areas within the tooling. So as you look at it there, you've got all the cables you can see in the middle of the screen. That is a heater cartridge on the end of each one of those cables. So we've got really quite dense ability to add power, and really quite good ability to control the temperature in each part of the tool as we wish. It's a fully enclosed system that is in operation. As you can see, there's an inherent lack of smoke. It's fairly clean from an operator's perspective. It's also, as a line, you can incorporate the standard sort of what we would call pre-preg additions. That is, edge trim, tape fitting. A lot of this material will go to be slit into narrower tapes for downstream processing. That can be integrated to the line. It simply isn't in this case. And one of the more important things, and I say this with a tongue firmly in cheek, is that it is very easy to clean. The whole tool opens up a little bit like a book. That's what the hand wheel in front of the picture is for. Undo 4 bolts, and you can open up the tool and clean out any old polymer, any degraded polymer, and basically start again from fresh. So I'm about to summarise, but we've got some numbers which I keep being asked for. The fibre area weight, we're down to 150 GSM. That is simply a question of how many bobbins we feed into the system. We're running about 50% of fibre volume fraction, and I must add at that point, that's more to do with the polymer being used and the lack of voids. The actual fibre volume fraction we use is simply it's a number on a HMI. Change the amount of polymer you add and your fibre volume fraction will change. It's not rocket science. We are saying 50% because that, with the polymers we've been using, is the point at which we start to see an unacceptable amount of voids in our microscopy, whatever. We run at line speeds of 10 meters a minute, demonstrated. The line you just saw on the previous slide is rated to 20. Again, depends hugely on the viscosity of the polymer at the melt temperature, and essentially what your tolerance to voids is. It will, of course, being electrically heated, process any material up to 450 degrees centigrade. The key sort of process variable thereafter is the temperature of the finishing rolls, which has an effect on the microstructure of the polymer. It's a small footprint. The line that we have got now, including the creel, fits in our second processing room, if you like, here at Texkimp, and that room is only 5 meters by 10 meters long. So it's not a large machine. It's very simple to use, and beyond actual process development and process tuning, an operator might need probably less than half a day of training to be able to run a machine and run it safely. It also requires minimal support infrastructure. It sits in a standard factory floor, standard extraction, nothing really excessive about its requirements apart from perhaps power, depending on the size of the machine. And again, you can integrate the standard optional elements like slitting, edge trim, handling, beat scanners, and so on to really add the finishing touches to a line. And that brings me to the end of my presentation. Thank you. Thank you, everybody, for listening.
Thank you, Andy. Another excellent presentation, and I'm sure you'll be available on one of the tables later to take any questions or chat with the participants today.
Absolutely. Look forward to it.
Okay, so we've had some great presentations from those shortlisted for our 3 innovation awards. I'd like you all to switch your microphones on now if you can, and join me in thanking Richard Thompson, Dominic Hopwood, Samantha Bunyan, Alan Banks, Peter Quigley, and Andy Whitham for the presentations today, and wish them all the best of luck through the awards process. So if you can, a round of applause, please.
We can do some emoji reactions, some claps.
Oh, super. So, as I said earlier, we will be announcing the winners of the awards on Wednesday, 18th of November, through our social media, through press releases, and there will be a supplement in the Materials and Manufacturing Technologies magazine. That will be not just for the Innovation Awards, the shortlisted candidates are presented on today, but the wider industry awards as well. That's very exciting. I wish you all luck with the awards next week.